Hello everyone, today I will be presenting our technical report for the LLM and RAG course. The project is titled LLM Generated Text Detection, a systematic comparison of traditional ML and transformer approaches. Our team chose the Kaggle competition LLM Detect AI Generated Text, where we developed a pipeline that achieved a public AUC of 0.9598 and a private AUC of 0.8728. Let me walk you through our journey. Here is a quick roadmap of the talk. We will cover 6 areas: the problem setup, our data and 2 main algorithmic pipelines, traditional ML and transformer-based, our iterative experimental journey, and finally a discussion and conclusions. The whole presentation is organized to tell the story from a simple baseline to our best final system. This is a binary text classification problem. Given an English essay, the model must output a probability that it was AI generated. Performance is measured by the area under the ROC curve. An AUC of 1.0 means perfect discrimination, 0.5 is random. The competition uses a two-phase evaluation. The public leaderboard used only 25% of the test set during the competition, while the private leaderboard, which determines the final rankings, used remain 75%. This distinction became very important in our work, as we saw cases where public and private scores diverged significantly beyond the modeling challenge. The competition imposed 4 hard engineering constraints. First, everything, training and inference, must run inside a single Kaggle notebook. Second, internet access is disabled, so all model weights and datasets must be uploaded in advance. Third, this is a strict time limit: 9 hours for GPU and 12 for CPU. If the notebook times out, no scores is recorded. Fourth, for reproducibility is required. This constraints shaped every design decision we made. The official training set contains only 1,381 essays, and critically, only 3 of them are AI generated. This extremely class imbalance makes it nearly impossible to train a useful classifier on this data alone. As you can see in the panel A on the left, to address this, we incorporated the public available DAIGT v2 external dataset, which contains probably 45,000 balanced essays, roughly equal numbers of human writing and AI-generated text, where the AI content was produced by the models like GPT 3.5, GPT 4, Cloud, and Llama. After merging and deduplication, our total training set grew to 44,868 samples. The effect is dramatic. As shown in panel B on the right, the public AUC jumped from 0.626 to 0.838. Improvement of over 0.21 points. The private AUC dipped slightly. We tripped to a mild distribution mismatched between DAIGT v2 and the competition's private test set, but the overall lesson is clear. External data is essential for this task. We applied standard pre-processing, white space trimming, duplicate removal, short text filtering, and label normalization. We deliberately avoid aggressive augmentation techniques like back translation, which we found caused overfitting in our experiments. Our traditional pipeline starts with tokenization and feature extraction. The key design choice, we train the BPE tokenizer on the test set only, not the training set. This aligns the vocabulary with the actual prediction domain and reduced distribution shifts. Vocabulary size is 49,536, chosen by Optona. The tokenized text is then converted to TF-IDF features with 3 modification sublinear TF scaling to reduce frequency domain names, smooth IDF to handle the real terms, and L2 normalization for length comparability. We use n-gram ranges of 3 to 5 subwords, capturing the local phrasal patterns, characteristic of AI-generated text. The third state is of soft voting ensembles of 4 models, multi-knowable naive Bayes, SGD with modified Hube laws, LightGBM and CatBoost. Instead of equal weights, we ran 500 optimal trains to find the optimal weighting for each model. The final prediction is their normalized weighted average consistently outperforms any single model alone. We use DeBERTa v3, which improves on BERT with disentangled attention, separate matrices for content-to-content and content-to-positions relationships. We work with 2 variants, the base model with 140M parameters as the teacher, and the small model with 70M as the student for distillation. Fine-tuning used 3/4 cross-validation, RW at learning rate of 1e-5, and for FP32, DeBERTa v3 is numerically unstable in FP16, producing frequent non-losses. We handle this with great normal clipping to skip bad optimization steps. The training curves show loss converging steadily, validation AUC reaching 0.9999 after 2 efforts and non-production events, dropping from 200 in April 1 to near 0 by April 3. Because the base model timed out on Kaggle, we distilled it into DeBERTa v3 small. The distillation loss combines cross-entropy on labels and MSE on logics, which did equally. Final late fusion, 85% TF-IDF, 50% DeBERTa. The classical pipeline dominates, despite V 9.1 to 9.5 all timing out, V 9.6 256 token inference kept resolved it and paradoxically improved the private AUC. Our experimental process spanned over 2 months and produced more than 30 different model versions. Let me walk you through the 5 major phases. Phase 1, V0, was a simple baseline, word level, TF-IDF plus logic regression on the official data only. This gave us a public AUC of just 0.626, barely better than chance on the private set. Phase 2, V1.0, introduced the DAIGT V2 external dataset. This single chance drove to the public AUC to 0.838, the largest single gain in the entire project. Phase 3 covers V2 through V7, where we explored multi-channel TF-IDF, handcrafting linguistic features, and various ensemble strategy. Private AUC remained around 0.69. Phase 4, the V8 series, was triggered by an external event. Kaggle upgraded their standard Python environment from 3.10 to 3.12. This broke our pipeline. We saw dropped scores and CatBoost capability areas. We had to completely retune everything for the new runtime. The result was worth it. V8.1 achieved private AUC of 0.873, a jump of more than 0.18 points over the best pre-V8 model. Phase 5, V9, added DeBERTa V3, version V9.1 through 9.5 all timeout. The breakthrough came with V9.6, where we truncated inference sequence from 512 to 256 tokens. Surprisingly, this gave us the best private AUC of 0.8728. Here is a summary of our results. The biggest single jump came from adding DAIGT v2, the Python 3.12. Recalibration in V8.1 pushed private AUC to 0.873. Our final 9.6 achieved private AUC 0.8728, the best of all versions. Overall improvement from baseline to final 0.188 AUC points on the private leaderboard. 3 key takeaways. First, the public-private gap. Public LLB sees only 25% of data, so don't over-optimize for it. Second, DeBERTa got just 0.15 weight in our fusion, because traditional machine learning is more data efficient at this 45,000 sample scale. Third, in version 9.6, we trained on 512 tokens, but inferred on 256. Surprisingly, this improved the private AUC, suggesting truncation acted as regularization. To wrap up, external data is essential. Traditional machine learning stays highly competitive. Transformer provides only marginal gains here. Distillation and inference truncation was key engineering tricks, and environment consistency matters. Final system: public AUC 0.9598, private AUC 0.8728, with the best private score from version 9.6. Thank you for watching.